Here we are going to prove a theorem. Prove that homomorphism of V and W is a vector space over F under suitable operation. Okay, so here we are going to prove homomorphism of V comma W is a vector space over the field F. Okay, so under suitable operation means what? Here you are using addition as an operation here to prove this theorem. Okay, so here, okay, what you are going to do is, they asked us to find homomorphism of V comma W is a vector space, right? We have a definition. In the previous video, I explained the definition for vector space. If you want to say a set as a vector space, few conditions should be satisfied. This set should satisfy some of the conditions. So here you are proving those conditions to say this homomorphism of V comma W is a vector space. Is that clear? Yeah. Okay, let's see. Before that, you are taking, what you are doing is, you are taking an element from homomorphism of V comma W. Okay, you are taking an element that is S plus T, and you are going to say this S plus T belongs to this homomorphism of V comma W. That is what you are going to do first. Okay, yeah. So let's see what is going to happen next. So you are taking two elements. S and T belongs to homomorphism of V comma W. So now using this two elements, you are defining something. You are defining small v of S plus T. This S and T should be capital letters, okay? Because these two, you are taking two elements from this homomorphism of V comma W. So all the elements in homomorphism of V comma W will be the functions. Usually you denote functions as capital letters. So here S and T is a capital letter, okay? I mistakenly wrote it as a small letters. So that's wrong. You should use capital letter for the elements you are choosing from homomorphism of V comma W. Okay, define like this. You will use this in the further steps. This plays a key role, okay, in this proof. Okay, so here next you are going to prove S plus T is an element of homomorphism of V comma W. So to prove that, what you are doing is, you are taking two elements from the vector V. V1 comma V2 belongs to capital V. Okay, here what you are doing is, you are going to prove two conditions. These two conditions are the conditions to prove homomorphism. Okay, so this and this will be in that format. What and what? This and this. Okay, are the conditions to prove homomorphism. Okay, okay. Let me start explaining this. So here you are going to prove this. Okay, for that consider this. Consider this, and at the end you will bring this. Okay, okay. Consider V1 plus V2 of S plus T is equal to, here you are writing this in this format. Okay, so here in the place of V, we have V1 plus V2, right? So write V1 plus V2 into S. First element is, okay, then plus, put plus, then the place of V, here we have V1 plus V2, so put V1 plus V2 into, then second element, right, T, here also T, so put that, then multiply this, okay, V1S plus V2S, then this plus, then V1T plus V2T, right? After that, what you are doing is, you are writing V1 terms in as one group and V2 terms as another group. Is that clear? Is that clear? Okay, you are writing like that. Now you are taking V1 common from this, so you get this, and then from here you are taking V2 common, so that you get this. So finally you proved, right? Considering this at final, by considering this, in the final you proved this, right? So one condition is verified. And the next condition, second condition for homomorphism is, next to prove alpha V of S plus T is equal to alpha into V of S plus T. Here alpha belongs to F, right? Okay, so this is what you are going to prove. Okay, so for that you are considering, this is the second condition for homomorphism. Okay, you are taking this, okay, considering the left hand side. So alpha v of s plus t is equal to, how you are writing this? Using this, you are defined like that, right? In this format you are going to write this. In the place of v, here we have alpha v, right? So put alpha v into, in the place of s, here we have what? S. So alpha v into s plus, here alpha v, right? Alpha v, right? In the place of v, we have alpha v. So alpha v into t. Okay, you are writing in that format. Next, what you are doing is, taking alpha outside. Okay, alpha separately and another two terms in one group, in one bracket. Okay, you are writing like in this format to bring the proof, to bring our result. Okay, this is an adjustment you are making to bring your answer. So plus alpha into vt in one bracket. So now from these two terms you can take alpha common, right? So I'll take alpha common so that you get vs plus vt. Now what you are doing, alpha, write this alpha into, from here you can take v common, right? So take v common into s plus t. So what you have proved, the second condition also we have proved. So from these two conditions, by proving these two conditions, you could say that s plus t is an element of homomorphism of v comma w. Now to prove a non-empty set as a vector space, you have to prove that set is an abelian group, right? Under addition, under operation addition. That is what our definition. So here you are going to prove this homomorphism of v comma w is an abelian group. Okay, so here let s comma t, you are taking two elements from homomorphism of v comma w. Now v of s plus t is equal to, okay, you are considering this v of s plus t is equal to, you are writing in this format. Okay, we defined like that, right? You are writing that as in that format. So v of vs plus vt. Okay, so here now you have to bring v of s plus t is equal to v of t plus s. Okay, that is s plus t is equal to t plus s. This is the condition for what? Commutative property, right? This is the commutative property. If you prove commutative property, then you can say that is an abelian group, right? That set is an abelian group. So here that is what you are trying to do. So for that you are considering this, and from this, by our definition, you have write this. What definition? You defined it, right? From this you are writing this. Now after that, just changing the place of the terms and writing. Okay, vt plus vs. So from this you can take a v common, so you get t plus s. So left hand side is this and right hand side is this. From this you can cancel v and v, so that you get this. So this commutative property is true, right? So that you can say homomorphism of v comma w is an abelian group. Okay. Next what we are doing is, you are going to prove, you are going to use alpha s when proving the condition for vector space. Okay, in the condition of the vector spaces, you will have alpha s. So here, so before proving that, proving homomorphism of v comma w is a vector space, you have to tell this alpha is also an element of homomorphism of v comma w. Okay, so for that, for this alpha is also, what you are doing is, first you are defining something like we have previously did. What you are doing, you are defining something like that. V of alpha is equal to alpha of vs for all v belongs to capital V. Okay, similar to the previous part. Okay, so here you want to say alpha is belongs to homomorphism of v comma w. So define v of alpha is equal to alpha of vs for all v belongs to v. So let v1 comma v2 belongs to what? Capital V. Okay, we are considering all these things are our choice. Next, what you have to do? Homomorphism. Here also you are proving homomorphism conditions. Here you are saying alpha s belongs to alpha is the s is the element that belongs to homomorphism of v comma w. This is what you have to prove, right? So for that, in the previous part you put s plus t. Here you, because in that part you have to say s plus t is an element of homomorphism of v comma w. So here you have to say alpha s is an element of homomorphism of v comma w, right? So for that, the place of s plus t, here in the place of s plus t, you are putting what? Just alpha s. Is that clear? So to proving homomorphism conditions here, v1 plus v2 of alpha is equal to, this is what you are going to prove. So you are considering the left hand side, and from this, how you have written this? You have written this from our definition. From the way we have defined, okay, you are writing similar to this format. So alpha of, here we have v, so you put v, right? Here is v, but in the place of v, here we have v1 plus v2, right? So you have to put v1 plus v2 into s. You are writing in this format. So alpha of v1, just multiply v1s plus v2s, so that you get, just multiply this also in the next step. Alpha of v1s, put v1s in one bracket, okay, plus alpha of v2s in one bracket. So from this you get what? Take v1 outside and alpha in. So you get this. So that the first condition is verified. And the second condition is, if lambda belongs, you are taking a scalar, that is lambda, to prove this condition. You need a scalar, right, to prove the second condition of homomorphism. So you are taking lambda belongs to f. Already in the previous part you took alpha. So here you should not take alpha. You may get confused, right? So that is why here you are taking lambda. Lambda belongs to f, and you are going to prove this. So consider left hand side. So you are writing this in this format. Okay. So just write it down, and alpha of lambda, put this 2 in one bracket, then alpha of, take lambda outside and alpha in, okay? So write like that. To bring our right hand side, you are making this adjustment, okay? Then that is equal to, okay? You are taking alpha in and lambda outside, so you get this, and from this you can write alpha of v, take v, in this step you are writing alpha and s in one as one group, okay? Take v outside. So like that you have written. So from this, what you have got? You have proved the second condition of homomorphism also. So from this you can say alpha s is also an element of homomorphism of v comma w. Now you are going to prove the major thing, okay? This is the important part in this proof. So that till now you have proved the necessary elements, okay? Till now what you have said is, these are the elements are in the homomorphism of v comma w. That is what you have said. So now what you are doing is, you are going to prove homomorphism using that elements. You are going to prove homomorphism of v comma w is a vector space over the field f. So for that you are taking 2 elements from similar to that. Let just take 2 elements from homomorphism of v comma w. Now we are proving 4 conditions, okay? 4 conditions. Already we have learned the 4 conditions for homomorphism, to say any set as a vector space. So these are the 4 conditions. So here is the first condition, okay? This is what you are going to prove. You will prove that, okay? It is very similar, so it is very easy, okay? Consider the left hand side, and is equal to, you are writing this, how you are writing this? You are writing in this format, okay? Alpha outside and b in. No, you're writing in this format. Okay. So from this you can write alpha of Vs plus Vt. So here multiply alpha in the next step. So alpha of Vs plus alpha of Vt. So alpha, take V outside, alpha is in one bracket. So V of alpha is plus V of alpha t. So from this you can say V and take V and V common, so that you get V of alpha s plus alpha t. So here what you can say, left hand side is equal to this value. You got this, right? So you have proved the required condition. So here in the next step, here you get V alpha of s plus t. I got nervous, so I am committing mistakes. V alpha of s plus t, right? This is in the left hand side, this is in the right hand side. So from this you can cancel V and V, so that you get this. So you have proved the first condition for the vector, to say any set as a vector space. So here is the second condition. This is what you are going to prove now. So consider the left hand side. You have to memorize these, okay? Understand it first, then memorize it. Okay? Because conditions, we have to memorize the conditions, right? Then only you can prove it. Okay. So consider the left hand sides is equal to, so from this you can write what? Alpha of b in the outside, v and alpha plus b separately, and bs as in a separate group. Okay, you are writing in that format. So from this you can write alpha vs. Here you are what you are doing is you are writing this in this format. Okay, am I right? V of s plus t. No, the element from the outside. So here alpha plus b. No, you are writing this in this format, I think. The element from the outside, v of alpha s is equal to alpha of vs. So here what we are doing, let me check. Okay, let me check. So here what we are doing, you are writing, you are writing in, this is in this format, the element, yes, this is this, you are writing this in this format. Okay, is that clear? Have a look at this, you can understand. Okay, this format looks similar to that. Okay, so here what you are doing, alpha into vs plus beta into vs, just multiplying. You will do that, right? Yeah. Now here taking v outside and alpha is s in one group, plus here also taking v outside, beta is as in a one bracket. So here from this you can say what? From this you will get this value. So second condition is also what? Proved. Now you are going to prove the third condition. Third condition is v alpha of beta is equal to v of alpha bs. Okay, so consider the left hand side. So from this you can write, take alpha outside, v in, and beta s in one bracket. Okay, here is nothing to get confused. Everything you are writing in this format. Okay, the element, this can be written as alpha outside and other elements in one bracket. Okay, you are writing in that format. Okay, you have to concentrate in that, how they are writing. So alpha of beta, take beta outside and vs. Why we are doing all these stuffs? The reason is because you need to bring the right hand side, right? So that is why you are doing all these things. Okay, alpha outside and take beta outside this small bracket and put this v in. So you get this beta of vs. So from this you can write alpha beta in one group and vs in another group. So from this you can say take v outside, alpha beta into s. You can write like this. So you have proved left hand side is equal to right hand side. So for this condition is also proved, and this is the final condition to say a set as a vector space. So here you are taking V of this. This is what you have to prove. So you are taking one unit element from where you are taking this unit element. You are taking this unit element from capital F. Okay. So consider the left hand side is equal to, this can be written as, write this one outside, into Vs. So from this you can, 1 into Vs is Vs, right? Yes. So from this what you get, the left hand side we have 1 into S is equal to Vs. So V and V get cancelled, so you get this. So all the 4 conditions were satisfied to say any set as a, any non-empty set as a vector space. The 4 conditions are satisfied here for homomorphism of V, W, right? So you can say homomorphism of V, W is a vector space over the field F. Hence the proof. Okay, so this is very simple. What you have to do is, you have to remember what are the things that you are doing. Okay, in step by step manner you have to know. First you are saying S plus T is an element of homomorphism of V, W, and then you are saying alpha S is an element of homomorphism of V, W, and using that 2 elements you will prove the conditions for the vector space, right? So the 4 conditions you are proving. At the end you will say that homomorphism of V, W is a vector space. This is our proof for this theorem. I hope you understand this, and I believe that you feel easy after listening this video. So thank you for watching.